The Kuiper Belt is not empty. James Webb just proved it. For decades, the region beyond Neptune has lived almost entirely inside equations. A flat disk of frozen debris wrapped around the outer solar system, sitting between 30 and 50 times the distance from Earth to the Sun. We thought we understood it. We had visited its most famous resident, Pluto, with New Horizons in 2015. We had detected hundreds of smaller objects from ground-based surveys. We called it the source of short-period comets and moved on. Then the James Webb Space Telescope turned its mirror outward toward that frozen frontier. And what it is finding is not the simple, flat, well-behaved disk the textbooks described. The Kuiper Belt has structure we never predicted, chemistry that breaks our models of how the solar system formed, and objects so large, so strange, and so numerous that the picture assembled over 50 years of observation is being redrawn from the beginning. This is the story of how the second most distant region of our own solar system stopped being a catalog and started becoming a place. The Kuiper Belt was predicted before it was found. In 1951, the astronomer Gerard Kuiper suggested that the region beyond Neptune might contain a population of icy bodies, remnants from the formation of the solar system that had never been incorporated into a planet. The prediction sat largely untested for 4 decades. Ground-based telescopes of the era lacked the sensitivity to detect objects small, dark, and distant enough to populate the outer solar system. Then in 1992, astronomers David Jewett and Jane Liu discovered the first confirmed Kuiper Belt object, designated 1992 QB1. It was small, faint, barely detectable even with the instruments of the time. But it was there, and it was where Kuiper said something should be. Over the following decades, survey after survey added to the catalog. Hundreds of Kuiper Belt objects were identified, then thousands. The picture that emerged was orderly. A flattened disk of icy bodies extending from roughly Neptune's orbit outward to about 50 astronomical units from the Sun. Most objects were small, a few hundred kilometers across at most. The belt was thought to be relatively chemically uniform, cold, static, well understood. Then New Horizons arrived at Pluto in 2015, and the orderly picture began showing its first cracks. Before New Horizons, Pluto was a dot, a point of light that even the Hubble Space Telescope could barely resolve into more than a fuzzy blob with vague surface markings. The July 2015 flyby changed everything. Pluto had mountains of water ice reaching 3,500 meters in height. It had a vast nitrogen ice plain, informally named Tombaugh Regio, the size of Texas, smooth and young, geologically active. Young. On a world 40 astronomical units from the Sun, with almost no internal heat source and temperatures near 230 degrees Celsius, there was fresh geological activity. The surface should have been ancient, cratered, undisturbed. It was not. Something was resurfacing Pluto. Something was driving convection in its nitrogen ice. Something was keeping this world geologically alive 4.5 billion years after it formed. The models had not predicted any of this. Pluto was supposed to be a frozen, geologically dead relic. Instead, it was a world with weather, with active surface processes, with a complexity that rivaled objects many times closer to the Sun. If Pluto, the best-studied large Kuiper Belt object, was this different from every prediction, what did that say about the rest of the belt? The answer, it turned out, was everything. The James Webb Space Telescope was not designed to study the Kuiper Belt. Its primary mission targets are the earliest galaxies, star-forming regions, and exoplanet atmospheres. But the same instruments that detect the atmospheric chemistry of a planet 500 light-years away can detect the surface chemistry of a frozen body 40 astronomical units from the Sun. In 2023, Webb pointed at Eris, the large Kuiper Belt object, whose discovery in 2005 triggered the reclassification of Pluto as a dwarf planet. Eris sits even farther out than Pluto, currently near its maximum distance of about 97 astronomical units. What Webb's NIR-SPEC instrument returned was not what the models predicted. The surface of Eris is covered in methane ice, that was known. What was not known was the state of that methane. Webb's spectral resolution revealed that the methane on Eris is not simply frozen methane deposited on the surface. It shows isotopic signatures consistent with methane that has been processed by cosmic radiation over billions of years and then revolatilized, vaporized and refrozen, in ways that require the surface to have undergone thermal cycling. Eris, at the edge of the solar system, in temperatures close to absolute zero, has been cycling its surface chemistry. The cold is not preventing chemistry. The cold is the medium in which chemistry occurs. This matters because it means Kuiper Belt objects are not passive frozen archives. They are active chemical systems evolving over geological timescales, through processes we are only beginning to characterize. In January 2019, New Horizons flew past a Kuiper Belt object that had been given the formal designation 2014 MU69. The team named it Arrokoth, a Powhatan word meaning sky. Arrokoth is small, roughly 36 kilometers in its longest dimension. It sits about 44 astronomical units from the Sun. Its shape is what made it scientifically extraordinary. Arrokoth looks like a snowman. Two lobes, one larger, one smaller, connected at a narrow neck. The larger lobe nicknamed Ultima, the smaller, Thule. The two lobes are the same color, the same composition, and their surfaces show no evidence of the violent collision that would be expected if two separately formed bodies had crashed together. The connection is gentle, the seam is smooth. The two lobes appear to have drifted slowly together from a position of originally orbiting each other, gradually spiraling inward under their own weak gravity, until they made contact at nearly zero relative velocity. This formation mechanism is called pebble accretion or gentle accretion. It requires that the two lobes formed from the same local cloud of material, not from bodies that formed in different places and later collided. The implication is profound. Arrokoth is a pristine record of the solar system's formation process. It formed from the same small cloud of material, gently, locally, without the violent collisions that shaped everything closer to the Sun. And its chemistry, measured by New Horizons and followed up by Webb, shows organic compounds, tholins, complex carbon-based molecules formed by cosmic radiation, processing simple ices over billions of years. The building blocks of organic chemistry were present in the outer solar system from the beginning. They have been sitting in the deep freeze largely unchanged ever since. The standard model of Kuiper Belt formation predicts a smooth distribution of object sizes, many small objects, fewer medium ones, very few large ones. Webb is finding that the large end of the distribution is more populated than any simulation predicted. Quaoar, a Kuiper Belt object discovered in 2002, is roughly half the diameter of Pluto. It has a moon, Quaoar, and in 2023 astronomers confirmed it has a ring system. Not an unusual ring system. A ring system that exists at a distance from Quaoar, where no ring system should be able to survive. Rings form when material orbits a body at distances where the tidal forces from the central body prevent the material from clumping together into a moon. This region is called the Roche limit. Beyond the Roche limit, ring material should coalesce into a moon. Inside it, material stays dispersed as a ring. Quaoar's ring sits well outside the Roche limit. By the rules that govern every other ring system in the solar system, Saturn, Uranus, Neptune, Jupiter, the ring should not be a ring. It should have become a moon long ago. It did not. It is still a ring. The explanation that best fits the data involves Quaoar's extreme cold. At that temperature, ring particles that collide do not stick together. The impacts are too elastic, too bouncy, to allow accretion. The cold is preventing the ring from becoming a moon. This is a mechanism that was not in the models. It required Quaoar's ring to exist as an observed anomaly before anyone thought to propose it. The Kuiper Belt is producing discoveries that require new physics to explain, not modifications of old physics. Beyond the classical Kuiper Belt, between roughly 50 and 1,000 astronomical units, lies a region called the scattered disk. Objects in the scattered disk have highly elliptical, inclined orbits, the signature of having been gravitationally scattered by encounters with Neptune during the early solar system. Sedna is the most famous member. Discovered in 2003, It has a perihelion of 76 astronomical units. Closer than its orbit should allow for a scattered disk object, and an aphelion reaching nearly 940 astronomical units. Sedna's orbit is so extreme that no known object in the solar system can account for it. Neptune's gravity does not reach that far. The standard scattered disk formation models do not produce Sedna's orbit. Something else puts Sedna where it is. Several explanations have been proposed. A passing star in the early solar system that gravitationally perturbed the outer solar system during the Sun's birth cluster. An undiscovered large planet in the outer solar system, Planet 9, whose gravity is shaping the orbits of extreme trans-Neptunian objects. Or a combination of processes that the models have not fully captured. Webb's observations of Sedna and similar extreme objects are building a more detailed chemical and physical profile of this population for the first time. The spectral signatures Webb is measuring are different from both classical Kuiper Belt objects and objects that have passed through the inner solar system. The extreme objects appear to carry a chemical fingerprint consistent with formation in a colder, more volatile, rich environment than the classical belt. They are not just dynamically different, they are compositionally different. Here is the possibility that is hardest to sit with quietly. During the Sun's formation, it was embedded in a star-forming cluster, a dense region containing hundreds or thousands of young stars in close proximity. Gravitational interactions within that cluster could have transferred material between forming planetary systems. Icy bodies from other stars' protoplanetary disks could have been captured by the young sun's gravity and incorporated into the outer reaches of our solar system. When Oumuamua passed through the inner solar system in 2017 and Comet Borisov followed in 2019, they demonstrated that interstellar objects traverse our solar system regularly. Most pass through and leave. Some, statistically, should be captured. Models of the early solar system suggest that a non-trivial fraction of the objects currently residing in the outer Kuiper Belt and scattered disk may have formed around other stars. If this is true, the Kuiper Belt is not exclusively our solar system's material. It is partly an archive of other planetary systems, other stars' leftovers, captured during the chaotic early period when the Sun was still surrounded by its birth cluster. Webb's spectroscopy is beginning to look for the chemical signatures that would distinguish locally formed material from captured interstellar material. The isotopic ratios of certain elements differ depending on the stellar environment in which they formed. A definitive detection of captured interstellar material in the Kuiper Belt would be one of the most significant discoveries in the history of planetary science. It would mean we have access to material from other stars without sending a spacecraft anywhere. The material came to us. The current estimate for the number of objects in the Kuiper Belt with diameters greater than 100 kilometers is roughly 100,000. For objects larger than a kilometer, the estimate rises into the hundreds of millions. That density sounds crowded. The reality is the opposite. The Kuiper Belt spans an enormous volume of space. Spread those hundreds of millions of objects through that volume, and the average distance between any 2-kilometer scale objects is millions of kilometers. If you were standing on a Kuiper Belt object, you would almost certainly see nothing else nearby. The sky would be black and empty. The sun would be a bright star, not the overwhelming light source it is from Earth. The nearest neighbor might be millions of kilometers away, a journey that would take a conventional spacecraft years. This is the paradox of the outer solar system. It is simultaneously full and empty. Full in the sense that objects are present almost everywhere. Each object Webb characterizes is a single pixel in a picture that will take decades to assemble. But the pixels already assembled are beginning to form patterns that the original picture did not predict. No discussion of the outer solar system is complete without addressing the most contentious question in modern planetary science. Is there a large undiscovered planet in the outer solar system? The hypothesis arises from a statistical anomaly in the orbits of extreme trans-Neptunian objects. The most distant known bodies beyond the Kuiper Belt's outer edge Several of these objects have perihelia, closest approach distances to the Sun, that are clustered in a specific direction. Their orbital planes are similarly aligned. The probability that this clustering arose by chance from random orbital distributions has been calculated at roughly 0.2%, less than 1 in 500. The most straightforward explanation is gravitational shepherding. By an unseen massive object, a planet roughly 5 to 10 times Earth's mass, on a highly elliptical orbit, taking thousands of years to complete. Planet 9, if it exists, would currently sit somewhere between 400 and 800 astronomical units from the Sun. At that distance, even a planet significantly larger than Earth would be too faint to have appeared in existing sky surveys. Webb is not the ideal instrument for finding Planet 9. Its field of view is too small for the broad sky searches required. But the Vera Rubin Observatory, scheduled to begin full operations imminently, will survey the entire southern sky repeatedly over 10 years, reaching depths that could detect a planet at those distances if it exists and reflects enough light. If Planet 9 is found, it will require a complete revision of models of solar system formation. A planet that large could not have formed where it currently sits. It would have to have been ejected from the inner solar system during the chaotic early period of giant planet migration. The outer solar system would be revealed not as a simple remnant disk, but as a dynamically complex structure shaped by a violent rearrangement of the entire planetary system. Step back and hold the full picture. A disk of frozen objects extending from Neptune's orbit outward for billions of kilometers, containing hundreds of millions of bodies, harboring chemistry that breaks the models of solar system formation, possibly seeded with material from other stars, possibly organized by a planet we have not yet found. Not the flat, simple, well-understood debris field of the textbooks. Something layered, something chemically active in the cold, something that has been evolving in its own slow way for 4.5 billion years. And now, for the first time, a telescope sensitive enough to read the spectral fingerprints of objects at 40, 50, 90 astronomical units is turning its mirror outward and reading what is written there. Each spectrum Webb captures is a page from a document we did not know existed. Each chemical signature is a clue about a formation process that happened before the Earth was assembled. The Kuiper Belt was supposed to be a simple graveyard. It is not a graveyard. It is an archive, a library, and possibly a museum containing artifacts from other stellar systems that arrived here billions of years ago and have been waiting in the cold ever since. We built a telescope to look at the beginning of the universe, and in the process it turned around and looked at the edge of our own backyard. What it found there is stranger than what we sent it to find, and we are only at the beginning of reading it. Thanks for watching. See you in the next one.